All right, so we're going to start this off with a rather relevant example from more so, I guess, earth science than anything else. So the idea here is you can use these Boltzmann-style probabilities to predict a lot of observations that we have about the world around us. So I don't know if you're familiar with things like mountains, but the idea is if you're pretty far off the ground, uh, the air is thinner. You're less likely to find gas molecules at that additional height. Now, this actually does depend on the temperature that you're at. So for this problem, what you've been asked to do is how much more or less likely are you to find an ideal gas 1,000 meters off the ground than if you were on the ground? Uh, and here you're provided with a constant which deals with the mass and the Boltzmann constant multiplied by the temperature. Now, to do so, what we need to do here is we need to look at the energies. All of these relative probabilities are determined by examining the difference in energy between our two systems. So basically what we're going to do is we're going to start at position number 1 here on the ground, and we're going to go up to position number 2. That's 1,000 meters up in the air. Now, this does get pulled down by gravity, so you should be able to find the delta E for this transition here. If you recall for gravity, we do have a nice equation to find its energy. And for that relationship, our change in gravitational potential energy can be found by taking our force and dotting it with our displacement. Now, we've done this a bunch of times. Our force here can be found by taking the mass of our object and multiplying it by the acceleration due to gravity. And here, our displacement is literally 1,000 meters up in the air. Now, with these two things here, we can put them together and find delta U. We're going to take our force dotted with displacement, so x times x plus y times y. We're going to leave the mass in there, so we'll just leave the mass as a variable. And 9.8 times 1,000 with an extra minus sign out front is 9,800 for our delta U and SI units. So once you have this, what you can do is you can compare P2 divided by P1, just like in the formula. It's equal to a natural exponent to the negative change in energy, which is m times 9,800, divided by the Boltzmann constant times the temperature. Now, we can simplify this a little bit because what we are told here is we're told explicitly what m divided by kBt is. So we still have e to the negative 9,800. That still stays the same. But you're told that m divided by kBt is 1 times 10 to the negative 4. Right, so what you can do here is you can just take negative 9,800 times 1 times 10 to the negative 4. Take this multiplication, apply it to the natural exponent. And if you've done so correctly, what you will get is 0.375. So basically what that means is if you're comparing the probability of us finding something up in the air to the probability of being on the ground, the probability of being up in the air is only 37.5% when compared to you being on the ground. So if you find 10, or say you find 100 molecules on the ground, right, so if you take this and we extend it to a system of 100 molecules, if you have 100 molecules on the ground, you will only find, actually let's not do that, let's just switch this around. So basically if you have a system of 100 molecules, so let's say you're working with a system in which n is equal to 100, what that means is on the ground, you will find a differing number as we're up in the air. you only have 37% of what you found up in the air versus on the ground. If you're using 100 molecules, and so if you're using 100 in total, what that means is up in the air of that 100, you'll find about 27 up in the air versus finding about 73 on the ground. Uh, Basically, if you take the number that you would have up in the air and divide it by the number that you have on the ground, you'll get 0.375. Now, in terms of the relevance of this, what this quick little energy thing tells you is when you're up in the air, you're less likely to find molecules when you're on the ground. Now, you might ask, well, what's the relevance of this? Why does this matter? If you were to take a plot of atmospheric pressure versus altitude, you will see this exact relationship show up. Right? You literally measure atmospheric altitude versus the pressure or the rough number of molecules that you're going to have in the air. It is going to exhibit this same exponential style decay. Right? So you can figure out what it is. You can match up the theory to the experiment here, and it matches up very, very nicely.